All right, let's talk a bit about training now. So the LFM 2.5 training recipe is quite similar to what you can find elsewhere in terms of stages. We have pre and mid training, 28 trillion tokens. We have supervised fine-tuning, preference alignment, and reinforcement learning. And here you can see I'm talking about 28 trillion tokens. And I said that we released a model of 350M parameters last week. So yeah, we pre-trained a 350 million parameter model on 28 trillion tokens. If you're familiar with Chinchilla scaling laws, that might sound a bit weird because we're supposed to be compute optimal at like, I don't know, like maybe 1 billion, not even 1 trillion parameter, I mean. But it's actually not the case. And we see that the performance still grows when you scale the number of pre-training tokens. And there was a super interesting paper by Roberts et al. Published last week about the test time scaling laws. And you can see here how LFM 2.5 350M compares to their new scaling laws. You can see Chinchilla scaling laws here and the new ones that they proposed here. And actually, we did not pre-train the models on enough tokens. We should pre-train even more to be optimal according to their laws. But this is cool because more pre-training works, and it works even at the smallest scale, which is great because these models are a lot cheaper to train than much bigger models. And here you can see a comparison. It's not just for pre-training, it's like post-training models. And you can see that the LFM 2.5 model is significantly better than the previous version, LFM 2 350M, on a lot of different benchmarks. So you have knowledge with GPQ Diamond, you have instruction following with IF-bench, you have case report bench, which is data extraction, and also a lot of tool use with BFCL and Tau2 bench. With this model, it's only 350 million parameters. So what we wanted to do is we wanted the model to be very, very good at data extraction and at tool use. And the rest, if it's not the best model in code, it doesn't matter. Like, people don't use it that way anyway. Same for math. I think it's really nice to try to target some capabilities and not try to be like average on everything. All right, let's talk exactly about that. Post-training, small and big models, what the difference. We have pretty much the same stage, so this is not really in terms of stages that we see a difference. It's more about how you do it. So for supervised fine-tuning, it's better if you're actually quite narrow and you focus on some task. It's true for general purpose post-training, but it's also true if you do fine-tuning. So you can take one of these models on Hugging Face and just fine-tune it for a use case. And for example, you have a use case where you have a particular function that you want to call. This is great. This is an excellent use case. Like, the more narrow you can find it or design it, the better it is. Then we have preference alignment. So during post-training, we have our own on-policy length normalized direct preference optimization algorithm that we quite like. And preference alignment is very nice because it brings you general improvements. It's not just about benchmarks. It's really like overall, after preference alignment, the model is better, it sounds better, and this is really nice to be able to just improve it overall. And finally, we have reinforcement learning. And reinforcement learning is extremely efficient, even at very small scale. It's a really, really important technique that we use everywhere. And the main thing is that it's very narrow in terms of focus. So you want to have like as many environments, as many tasks as possible, and make sure that you generalize well thanks to this. And then for small models in particular, they're quite sensitive to cold start SFT data. So if you have a particular task in reinforcement learning, it's always good to have similar samples and a similar task in your supervised fine-tuning mixture. And this is good feedback that you can see during reinforcement learning. Something doesn't train very well. It's probably because you are missing some cold start SFT data. Maybe the task is too complex. There are different reasons, but you can try to start again from the supervised fine-tuning stage, add your data, and then see if it improves anything. All right, but there's